In this video, we're going to talk about absolute value and piecewise defined functions. Let's start with absolute value. Absolute value is a number's distance from 0 on a number line. And we take the absolute value of a number. Right? -2 is 2 units or 2 jumps away from 0 on the number line. And that distance is listed always as a positive number. Okay, so take that idea and apply it to a function. The absolute value function, you've probably done some work with the V shape before. If I plug in a positive number for x into the absolute value, I'm going to get that same number because the absolute value of a positive number is still positive. But if I plug in a negative number for x, I want to get a positive result. So the result that I get has the opposite sign of that negative number. I take the opposite of -2 and I get 2. So when I look on this graph at -2, the absolute value of that number is +2. So I actually have two categories or two parts of this graph, right? I have the right-hand side where I have the same number as x, y equals x. This is one piece. And then I have the left-hand side where if I kept the x and the y the same, the branch would be down here. But because I'm making the y values positive, it's reflected over the x-axis and it rises above. It's reflected above. So we've talked about transformations, and we've talked about putting a negative on the outside of the function reflects that function over the x-axis because the y values change from being negative to being positive. And that's what's happening here. That negative x that we see right there is reflecting the left side of the graph above the x-axis. This is also a piecewise function. We're going to talk about those in a minute because we have different equations that we use to calculate the y value depending on what the x value is. If the x value is positive, we take the same value as x. If the x value is negative, we take the opposite. Okay? So your book takes this a step further and says, okay, well, what if I want to find the absolute value of a function? If I want to take and make a function that's the absolute value of another function. So that same type of reflection, anything below the x-axis, because of the absolute value, is going to be reflected above the x-axis. So it reflects the parts of the graph with negative y's above the x-axis. Here's an example. Let's say we have the y equals x squared minus 3. We know a lot about this graph. It's a parabola shifted down by 3 units. Okay, if I wanted to form a new function where I take the absolute value of the right-hand side, the parts above the x-axis are going to remain the same, but the parts below the x-axis are going to be reflected up above. Okay, so the parts that are above the x-axis, I'm trying to be exact here, look like that. Those parts stay the same, but this little dip below the x-axis is going to be reflected. So instead of being at 0, -3, it's going to be reflected up at 0, 3. And 1, -2 gets reflected and becomes 1, +2. Likewise on this side, -1, -2. The x value stays the same, but the y value changes to become +2. And so we get that same parabola-like shape, but it's reflected over the x-axis. Okay, so if we wanted to list the domain and range for these, I think we did one similar to this in a previous video. But the domain goes from left to right. This graph stretches all the way from left to right. So all real numbers for the domain. For this graph, the range goes from bottom to top. The lowest point would be this point here at 0, -3. So we have a point there, so we're going to use the square bracket. And there is no highest point. It continues on to infinity. For this graph with the absolute value, the domain is the same. It's still going to stretch all the way left to all the way right, so all real numbers. But now, when we look at the range, the lowest points, there's 2 points that tie there. Because of the absolute value, the smallest y value we can have is 0. We have 2 points there, and we're going up to positive infinity. Okay, so I hope that gives you an idea of what the absolute value can do to the graph of a function. Right? It's going to kind of fold it onto itself as it reflects anything that's below the x-axis. Now let's talk about solving equations with absolute value. I always like to start with this really simple one just to give you the idea. So we said that the absolute value is a number's distance from 0. So if I'm solving an equation where the absolute value equals 5, that means whatever numbers I'm trying to find, their distance from 0 is 5 units away. So I could be 5 units on the right, or I could be 5 units on the left. And so I get 2 solutions. One that's uses the 5, right? And one that changes the sign to be -5. The way this connects to the graph, and one of the graphing methods that you could use to solve, I'm normally going to be looking for your algebraic methods, but there are a couple graphing methods that are discussed in your book, and this is one of them. This is called the intersection method, where you graph each side of the equation as a separate graph, and you look for the places where those two graphs intersect. So in this particular example, we're looking at the absolute value of x, which is the v, and y equals 5 would be this horizontal line where the y value is fixed at 5. So the two places where they touch are the -5, and +5, 5. For the intersection method, we just take the x values of those points where they intersect, because the original equation only has x's. So we get the same 2 results. So those 2 numbers that we get are really usually corresponding to the 2 sides of the v, one on each side. Okay, hopefully that gave you the kind of the conceptual idea. Here's some steps that you can follow. So to solve an absolute value equation, we're going to isolate the absolute value, separate it into those 2 cases, one for each side of the v, and then solve both. Okay, so for this example, let's do that. The first step would be to isolate the absolute value. So I would like to move this 5 over to the other side. So I'm going to subtract 5. And then I'm going to divide. This is really like a -1. Okay, and then I can divide this, I shouldn't say divide, separate this into 2 cases. So what's inside here, just like the x that we were looking at above, could be equal to 3, or what's inside here could be equal to -3, because the absolute value of -3 is also 3. So 4x plus 3 would be 3 itself, or 4x plus 3 would be negative 3. I like to use this method. I think it's the most direct and obvious method to me. However, you can also negate what's inside. And so if you do that, just make sure you negate both of the pieces that are inside. And in that case, you would keep a 3 if you negated the left-hand side. Either method works just as good, so I'm happy for you to use whichever you're used to using. Just make sure you're using the method correctly. So then we would want to solve each of these and get our two solutions. And we would reduce this one to negative 3 over 2. So we get two answers, x equals 0 and x equals 3 over 2. There are some special examples in your book where you have two absolute values set equal to each other. In that case, you're going to make your two cases by making them both positive, sort of like this, and making the left-hand side positive and the right-hand side negative. There's actually 4 possibilities, but they sort of overlap and they end up being just the two cases that look very similar to these. Okay, now let's look at the inequality. I like to do that same kind of simple example at the beginning here just to show you what the inequality stands for. So again, we'll go back to the distance on the number line. So if I have the absolute value of x, I want numbers whose distance from 0 are less than 5 units away. And I didn't have the equals bar here, just less than. So that's going to be numbers on this slide, like 1, 2, 3, 4, all the way up to 4.99999. And then likewise on the other side, the negative side, negative 1, negative 2, negative 3, all those would satisfy that up to negative 4.99999. So we have two parts here. X is less than 5, so any number less than 5, and at the same time greater than negative 5. So just like with the equation, we form our two cases. One is as is, this is the positive side. The second case, we're going to make the 5 negative, and we're adding, for the inequality, we're also going to be flipping the sign. I like to write out the two separate cases. For the and, which it'll be an and when we have the absolute value on the left and there's a less than, the shading turns out to be one section of the number line. And so all the solutions satisfy both of these equalities at the same time. We use the and for that. If you would like, you could also write this as a double inequality, because all the numbers we've shaded there are between negative 5 and 5. These two are the same. When we write our solution for the inequality, we're going to be using interval notation. This time we're not including the negative 5, so round parentheses, all the way up to positive 5, round parentheses. We could have a similar conversation for the greater than. Now we are looking for numbers that are more than 5 units away from 0, not equal to again, so we're not including the 5, but 6, 7, 8, 9, 10, all those would be included. Negative 6, negative 7, negative 8, negative 9, etc. All those would be included. So this means x values that are greater than 5 would be more than 5 units away, or x values that are less than negative 5 would also be more than 5 units away. If the absolute value is on the left and we have a greater than sign, we're going to see the solution separated into two parts. two shaded regions on the number line. This is why we use the OR. This one cannot be combined into a double or a compound inequality. It's not appropriate to do that because it's not in between. So our final answer, if we were to write it in interval notation, we're going to go from left to right. Goes from negative infinity up to negative 5. Again, round parentheses because the negative 5 is not included. Union, just after 5, up to infinity. Okay, so you can kind of manage what you're going to expect as your solution. If you have the absolute value on the left, if it's a less than, you know you're going to get one section. If it's a greater than, you know you're going to get two sections. And if you don't, you might want to look back and check because there might be something interesting about the problem or you may have made a small mistake somewhere. Okay, so let's solve an absolute value inequality. This one's from your book. It's number 55 in this section. The absolute value in this case is already isolated, so we don't have to do any work at the beginning. We can go directly to separating it into two cases. So the first case will be the same. 15 minus x is less than 7. For the second case, we're going to make the 7 negative and change the sign to a greater than. Okay, so then we'll solve each of these. Subtract 15. Because we have a negative x, we're going to divide both sides by negative 1. Don't forget, if you divide or multiply by a negative number, you have to flip the sign. So this becomes x is greater than 8. And this becomes x is less than 22. If you need to, you can draw a number line to help you visualize the final answer. I want numbers that are greater than 8. Notice, I'm going to go all the way back to the top. Notice at the top I do have a less than, so this is an and, which means I should get one section of the number line. So it's greater than 8 and at the same time less than 22. My final answer here will be the interval notation from 8 to 22. Because I don't have the equals bar, again, I'm going to be using the round parentheses. Okay, now there are some special cases that are discussed on page 126. This is section 2.4 in your textbook. Those, just, side note here. All right, so if I have an absolute value, and I want to know something like when it's less than or equal to negative 5. No matter what this is, I'll just put something in. Let's say it's x plus 2. Okay. The absolute value is always positive. It's never going to be smaller than a negative number. Right, so that's one of those special cases. So in this case, there would be no solution. Another one would be if we had the absolute value greater than negative 5. Same kind of logic, the absolute value is always going to be positive. It's always going to be greater than a negative number, no matter what the number is, no matter what's inside here. So in this case, the solution would be all real numbers. There are other special cases like this that you could dive into, okay? So maybe we'll give you a couple in class or something that you can try to work out. But overall, this is the basic idea for the absolute value. Okay, last, I want to take a second to look at piecewise defined functions. We've already mentioned them a little bit and given this definition, but I'll go ahead and read it again. So this is a function defined by different rules or formulas for separate sections of the domain, or for separate groups of x values. So I basically am cutting up a function and kind of taping or pasting two parts of two different functions together. Function describes a trend, and sometimes that trend changes. So this kind of follows with that idea. So let's say we wanted to graph this one. This is also from your book. It's number 6 in this section. It's 2.5. Let's say f of x is x minus 2 if the x value is less than 3. And f of x is 5 minus x if the x value is greater than or equal to 3. So at 3, we're kind of dividing it into two separate functions. Okay, so I usually make, if I'm making this graph by hand, I make two separate t-charts, one for each side. So if I'm using x minus 2 to calculate my y value, then I need to use x values that are less than 3. Okay, so maybe 2, 1, or 0 would work well. Let's go ahead and do that part. So if I plug in 2, and I plug in 1, and I plug in 0, I can plot those points. Now it's going to lead up to 3. Okay, maybe we should list that here. If I were including 3 minus 2 would be 1. I would include this point 3, 1, but I'm not including it. So really, this is going to show up as a whole on this part of the graph. Okay, so let's plot that. So we have 2, 0, 1, negative 1, 0, negative 2, and it's going to lead up to the point 3, 1. So I'm going to have a little open circle there. But I could go continue to the left. So I could plug in negative 1, negative 2, etc. It's going to keep going up. Because I can use any number less than 3. Okay, for the second part of the graph, when I use 5 minus x to calculate the y value, I'm going to be using x values that are greater than or equal to 3. So I'm allowed to use 3 and anything bigger. If I plug these in, if I plug in 3, plug in 4, plug in 5, I can plot these points. So I have 3, 2, and this is equal to here, so I know it's a solid point. 4, 1, 5, 0. Our graph doesn't go much beyond that, but we could plot any other x values that were bigger than 6, 7, 8, etc. Okay, so this is a piecewise function. It's two pieces glued together into one function. Another kind of common type of piecewise function is called the greatest integer function. And it has an interesting bracket notation. It's sort of like a double bracket around the x. And it represents the greatest integer less than or equal to x. So I put a number in there like 3.5. The greatest integer of 3.5. Basically, I'm going to round down. Remember, an integer is a positive or negative whole number. It's not a fraction, right? So it's less than or equal to. This is not a whole number, so the nearest whole number less than 3.5 would be 3. And that creates a graph that's kind of special. It is a piecewise function. Sometimes it's called the step function because it does look like steps. All right, I put a few spaces here. You could really make a gigantic t-chart to make the whole graph of this, but I'm just going to do a few so that you can see what it looks like. So let's say we did 0, 0.5, 0.99, and 1. Okay, so the greatest integer of 0 is an integer. So it's either the greatest integer less than that or equal to. Since it is an integer, it's going to be equal to 0. So when x is 0, y is 0. The greatest integer of 0.5, this is not an integer. So I'm going to round down to the biggest integer less than that. The closest integer less than that would be 0. The greatest integer of 0.99. Again, I'm going to round down to the closest integer less than 0.99, still 0. Okay, but then when I get to 1, it's an integer. So the greatest integer of 1 is 1. We could keep going, right? 1.5 would round down to 1. 1.99 would round down to 1. Okay, so each of these makes a little step. So at 0, 0, we have a point. We're going to, all the decimals in between 0 and 1 are going to round down to 0. And then it's going to lead up to the 0.01, but not touch it. So we put a little hole there to show, kind of like the round parentheses, to show that it gets infinitely close, but at 1, it jumps up to 1. Then the same thing happens again. Any decimal in between 1 and 2 is going to round down to a y value of 1. Notice we're at 1 now. It's going to get infinitely close to the point 2, 1, but when I get to the number 2 itself, I'm going to jump up to the next step. Okay, and it's going to follow this pattern, right, all the way. So we can continue drawing this all the way off the grid. It's going to keep going in this way. The same thing would be true for negative numbers. So any decimal between 0 and -1, remember it's going to round down. It's going to round down to -1. So -1, this is kind of hard because it feels backwards because it's negative. -0.99, -0.5, -0.001. Okay, it's going to round down to -1 until we get to 0 itself. Same thing here. Anything between -1 and -2 is going to round down to -2. And so the steps just kind of follow that same pattern. So this is called the greatest integer function. It's the greatest integer less than or equal to x. All right, well, I hope this was a good summary of these two functions. I hope you'll take some time to practice these ideas online, and we'll take any questions when we see you in class. Good luck.